In question 4 of our series, where we set up and solve differential equation problems, we're asked, suppose we have 7,000 liters of water with 50 kilograms of salt in it. If we add pure water at a rate of 2 liters per minute and add water containing 0.6 kilograms per liter of salt at a rate of 9 liters per minute, and we know that water flows out at a rate of 11 liters per minute, then what is the salt content as a function of time? Just to give you a scenario of what's happening, let's say we have a tank. And this tank is being filled in two ways. So we have one pipe that is releasing pure water at a rate of 2 liters per minute, and we have another pipe that is releasing salt water at 9 liters per minute. The tank itself contains 7,000 liters of water, and it has 50 kilograms of salt. So this tank contains 7,000 liters per 50 kilograms of salt. Not only that, water is leaving the tank as well, and it's leaving the tank at 11 liters per minute. So there's a hole, and water is leaving at 11 liters per minute. What I have to do is set up a function, and I'm going to call my function a, and it will be with respect to time, so a of t is equal to what goes in minus what goes out. Now, since we're talking rates here, we need to take the derivative of a, and the derivative of a of t is a prime. And since this is a differential equation problem, we're going to use the notation dA over dt is equal to what goes in minus what goes out. Let's start with what goes in. We know that fresh water is entering at a rate of 2 liters per minute. Fresh water contains no salt. Remember, they want our equation to model the salt content. So we need to know the amount of salt per unit time. 2 liters per minute of fresh water contains no salt. So this part, you multiply it by a factor of 0 kilograms per liter. Plus, something else is going in. And this part's important. We have 9 liters per minute of salt water coming in, and that has a concentration of 0.6 kilograms per liter. So if I multiply this number by 0.6 kilograms per liter, look what happens. We end up with mass at the top, the liters canceling out, and time at the bottom. Mass per time, amount over time. So this models the first part where we have 9 times 0.6, no need for the units to be included anymore. 9 times 0.6 is, as suspected, 5.4. Minus, now the more difficult part. We know that the tank holds 7,000 liters, but we don't know at any particular instant how much salt it contains. So I'll write down A for the amount over 7,000 liters. And I'm going to multiply this by the rate at which the water is flowing out, which is 11 liters per minute. The liters cancel out. The units for the amount is in kilograms per unit time, which is in minutes. So we have 11A over 7,000. This is our differential equation. It's separable. Let's go ahead and separate it, integrate, find our c, and conclude. We need all the a terms and the t terms on one side. And we can do that by first combining these two terms. We end up with 5.4 times 7,000. I'm finding a common denominator between 1 and 7,000. It's 7,000 minus 11a over 7,000. dA over dt. What I can do next is reciprocate both sides. So I'll have dt at the top, dA at the bottom, and similarly 7,000 at the top, and this expression at the bottom. I'm going to multiply 5.4 times 7,000. That's 37,800. 37,800 minus 11a. If I multiply both sides by dA, it goes over here. And there you go. I have dt on the left side, and the expression on the right side is exclusively in terms of a. Integrating dt gives me t plus c. I've placed the constant plus c on the left side because this equation is with respect to t. You put the constant on the side where it is in respect to. And on the right side, this is a little more complicated. We have to take out the 7,000. We did an example like this in question 1. And what we did is we did a u sub, where I substituted u in for this expression, differentiated. I got du is equal to, that went away, minus 11 dA, solved for dA, and I got du over negative 11. So the integral of 1 over u times du over negative 11 is the following. This negative 11 goes out here, so we have 7,000 over negative 11 ln absolute of what u is equal to t plus c. To find out what c is, we need to substitute in what a is at time 0. At time 0, a is equal to, let's find out. Suppose we have 7,000 liters of water with 50 kilograms of salt. So at time 0, before this process has started, we had 50 kilograms of salt. I'm going to substitute 0 into t, that takes it away, and substitute 50 into here. Let's go ahead and find c. So first I'll evaluate 37,800. 37,800 minus 11 times 50. Then I'll take 7,000 divided by negative 11 times ln of what I just found, and I end up with negative 6,697. Negative 6,697. Substituting this back into c, we end up with t minus 6,697 is equal to the right side here. Now, many teachers will expect you to solve for a. That's not hard to do. If you do solve for a, you're going to end up with an equation that contains Euler's number, e to the power of something. But like I mentioned, it's not hard to do. You divide both sides by this factor. It would end up over here in the denominator. And then you would raise both sides to the base of e. That would get rid of the ln, and then solve for a. There you have it. That is how to set up and solve differential equation problems.